Welcome. I'll just officially start here. So this lab is going to be fun. It's going to be challenging, which I think maybe, if anything, we all need a little bit of some challenge, and we need these virtual labs to make us think a little bit more than maybe they have in the last few weeks. So we had a nice warm up, but here we go. So those of you that are confused about the pre-lab, you are not alone. A lot of people struggled with understanding the concepts of this lab, and I'm one of those people. So I struggled with understanding exactly what the lab is asking. So with that being said, I have about 60 slides today for 50 minutes. So I'm going to move quick, and I'm not necessarily going to be able to promise everybody that you will know all the ins and outs of the lab the way we have in the last few weeks. We just don't necessarily have the time. So be prepared to have to work on this. But I'm going to tell you, before I even go to my slides, this one truth about this particular lab, which is it has an exceptional post lab. So the post lab really helps understand what to do with the data. So if after this lecture, you understand, okay, I understand the broad sense of how these reactions work, but I need more about the post lab and what to do with this data. There's a reason I'm doing this presentation this way, is because you will get that help. You'll have to just collect the data and trust me, but it actually does work out really nicely in the post lab, the data, and being able to know how to do, where to put the exponents, where to do that kind of logarithmic math, and the stuff that maybe worries us. So that's all built in nicely to this lab. What I think is not there is the understanding of how the three reactions we're going to look at together work together, how we are looking at one reaction to time a different reaction. There's all of these intricacies within this week's lab that I think are important to have our heads wrapped around before we collect data. Even if we're not 100% on what to do with the data, you have to going to have to trust me here. Without further ado, are there any questions before I dive in? I didn't expect so.
Wait,
all right.
Yeah,
go ahead. Abe, what's up?
I had a quick question on number one on the pre-lab.
Yeah, it's 65 mils, and I'm going to explain where that comes from in a little bit. But just it's basically V1 M1 equals V2 M2. So it's a simple dilution. So you're considering how many moles are in the solution, and then what the total volume is, right? Because you put a known molarity into your reaction, but you're mixing with other solutions. So the volume changes even though the number of moles doesn't change. And so the total volume ends up being 65 mils. So you end up figuring out how many moles of some reactant you put in, and then you divide by the total number of mils in the reaction, which is 65. And I'm going to show you that in just a second. And that's how you get to number one.
I was about to say, because I don't know where you get like 65.
I'm going to show you. I'm going to show you. The reason that I'm jumping right into the answer for your question is because a lot of the people who are already here are chuckling to themselves. I've had Zooms over the weekend. I've had emails. This is confusing to everybody. So Abe, you're not alone. You're a part of the collective, which is that this is confusing. So I'm going to show you where that 65 comes from in just a second. But I really want to highlight that what he's asking, I think we're all thinking, which is like, you know, there's a few steps that we're missing in the pre-lab information to understand it.
All right, gotcha.
Cool. Thank you for asking that question, actually. Okay, so today we're talking about kinetics, right? The speed of reactions. And so with just a little bit of preamble, we understand intrinsically, even if we haven't really thought about it, we know reactions take different speeds. Here is a car. There is iron in the car's metal, which is oxidizing with the salty air by the coast and is rusting, right? And this takes years and decades to do. So this is a reaction that goes very slowly. Meanwhile, the combustion of a lot of hydrocarbons with oxygen with the proper activation energy creates a very fast, kinetically very fast reaction where we have what we call an explosion, right? And so we understand that as reactants mix to create products, that can happen over decades. It can happen over milliseconds. And studying, and more specifically, timing those reactions is what today's lab is all about. So this diagram here shows the idea of if you had a simple reaction, A going to B, so just kind of the transformation with a standard set of time. And I think I really want to highlight that, this idea of two reactions going at the same set of time, because we're going to be looking at that today, keeping one time frame constant and looking how the rates change. But you can see that the top reaction goes all the way from all purple to all green within half of a clock, whatever that means. Meanwhile, blue goes to yellow, but maybe not even halfway. So every reaction under certain conditions will have its own kinetic rate, will have its own rate, its own kinetic analysis, and that's what we're looking at today. So what changes that rate beyond the individual reaction? If we have one reaction and we're studying a single reaction, what affects the rate of how quickly that car rusts or how quickly that explosion happens? So three things specifically that we want to talk about today, and of course, one thing importantly we're going to study. The first is the physical state. The molecules have to interact with each other to do the reaction. So if it's a solid state versus liquid state versus gaseous state, that changes the rate of reaction. Temperature is really important in reactions. Normally, we have to make sure, and today you'll see that we are going to emphasize keeping temperature constant because temperature changes the rate. But molecules have to have enough energy when they interact with each other to do the reaction. So the same number, the same concentration of reagents at a cold temperature will yield some amount of product, but at a higher temperature, that same concentrations might yield a completely different, a more, most likely, amount of product because they have more energy to do the chemistry. So temperature is going to dictate rate. But for today, the most important idea is that concentration affects the rate. The molecules have to find each other and interact. So the best way to think about this is to forget moles and forget the grand number of molecules we think of. I always like to go to 100. 100's easy for me, right? So if we have 100 molecules together, the reagents, and we have 50 of one and 50 of the other, you can imagine how often those molecules will be able to find each other, bang into each other, and create a product molecule. But if you change that statistical number, keep 100, but you have one of one reagent and 99 of another, then the odds might be different and change. So concentration, we understand you have to be able to find each other and interact enough to create these products. So the idea here is that the rate of the reaction is proportional to the collision frequency, how quickly, how often they find each other in the reaction, whatever physical state they are, solid, liquid, or gas. And that collision frequency is directly proportional to concentration. So I know that you're just getting into kinetics, and so I'm not going to try to over-explain the idea of kinetics, but you might have to go into your textbook and read that chapter. It's very good in the Tro textbook that explains these ideas. But simply put, if we graph concentration of a product A, or of a reagent A as a function of time, there's three, or we're going to talk about, and in the textbook we'll talk about, three different situations we can have. A 0th order reaction, a 1st order reaction, and a 2nd order reaction. And what that means is that with a 0th order reaction, the rate, and you can see in the second graph as a function of concentration, when you change concentration, the rate doesn't change. You can have more, you can have less, but how much product you make is indifferent to that concentration change. And that's a 0th order reaction. You would expect that if you graphed rate as a function of concentration, you get a straight line. Then you have a 1st order reaction, which is this green line, which as time changes and concentration changes, the rate changes, but it changes linearly as a 1st order reaction. Rate equals K times concentration to the 1. So you have a straight line, a linear line, when you graph rate as a function of concentration. And so you see that if you increase the concentration, you increase the rate. If you decrease the concentration, you decrease the rate, but that always happens at a linear rate. And then the third option that we have is a 2nd order reaction. And there's more beyond this, but this is where we will limit our scope for today's lab. And a second second order reaction changes exponentially or quadratically, how you want to think about it, as a function of concentration. So over time, as the concentration drops, the rate changes, but not linearly, to another order, so a second order degree. So you have this curving as the concentration changes, the rate changes, but not in a linear fashion. And those are the three options, and that's what we're kind of looking at. We want to know how fast a reaction occurs, but we also want to know the fundamentals within that reaction. And we call that the rate law. So the rate of a reaction can be expressed by this rate law. So if we have now a little bit more complicated of an idea for this reaction, but this is the very generic sense, where the lower cases are the coefficients, the upper cases are the reagents and the products respectively. And the idea is that we have A and B reacting to form C and D. And so the rate is how much the product, we're talking about how the concentrations of the reactants change the formations of the product. So the rate can be described as the rate that we will see our products being formed equals some rate constant K times the concentration of A to the P times the concentration of B to the Q. What are P and Q? Well, that's that order. So if it's 0th order, any concentration to the 0th equals 1. And so the rate has isn't affected by the concentration of A. Let's say P is 0. Then you would not have the rate be affected if you change the concentration. If the P is 1, then the concentration will change linearly. You increase the concentration of A, you increase the rate at the same linear proportion. And of course, P can be 2 as well, and then you would be changing it exponentially. So those are the options. And once we have P and Q, we know how the rate will change by the change of concentration of A or B, and we know the rate constant, then we can plug in any concentration of A and B, and we know exactly what the rate of that reaction will be. So this is a very, very powerful piece of information as we're studying chemistry to be able to predict not just how much product, but how quickly that product will be formed. So what do we do to solve for these P's and Q's? What we do is that we hold one constant. So we just change the variable A, but keep B the same. And by doing that, it becomes just a constant in our equation C. It's the same each time. And so then, because we have this exponent, and that's tricky to graph and to understand, we'll take the logarithmic form of this. And we remember from math, when we take the log of something with an exponent, the exponent comes down to the front of the log. So A to the P becomes P log concentration of A. Plus we have log K, which is a constant. That's the constant of our rate constant. And we have log C, which we just said we're keeping the same each time. So it's also a constant. So those are two numbers. They're the same numbers each time, whatever they are. We can combine them into a single constant, which we'll just call big C. Really confusing, and I wish I would have used a different letter there, but it's just a constant that equals the log C and the log K values. It's different for every reaction, but when we're holding B constant, then we just have some number that's added. And so the result is log times the rate equals P, that's the exponent, log A plus C. And when we graph that, we get y equals mx plus b form, where m, the slope, equals p, that exponent. So now what we've done is we've held b constant. We changed a up a little bit in concentration. We saw how the rate changed. We took the logs of the rate and we graphed that. And when we graph it, we should get a straight line where the slope is this exponent p. And then the intercept here is all of that junk. And we're not going to need to interpret that today. But what that intercept means is the log k plus the log of the thing that we're holding constant. So what we can do today, what we're going to do, not today, this week, but what we're doing in this week's lab is we are going to solve for P by holding B constant and measuring the rate at several concentrations of A. Then we'll solve for Q by holding the concentration of A constant and measuring several different concentrations of B. So those are kinds of two experiments that we'll do simultaneously. And then once we know the values of P and Q, and remember, it's going to be 0, 1, or 2, I promise you. And if it's a little bit off, we're going to round to the nearest whole number. We're just going to keep it that simple this week. Once we have P and Q, and we know any run, we know the rate, we know the concentration of A and B, we know P and Q, we plug all of that in and we can solve for K for each run. And we'll have 5 K values and we'll take an average. And that's what we're going to be doing today, is measuring the rate, changing the concentrations, calculating P and Q, and then at the end, once we have all of that, solving for K. Okay, so here is our reactions today. So we are going to be solving for this rate law. Rate equals K times the concentration of I minus to the P times the concentration of persulfate to the Q, and that's also peroxydisulfate. So I want to start out by saying that there is 2 names for this ion, and they are used both in the lab. So at times in the post lab, they use this one, and at times in the procedure, they use this word. They are the same. So that's going to be an important thing for everybody to take a note of before they dive into this lab. There's a lot of different names, different sulfates and iodides. So make sure that you keep track of those. But we are then looking at the reaction between iodide and persulfate, and that forms this triiodide and sulfate. This is the reaction we're studying today. But we can't see this reaction. It's a clear reaction to a clear reaction. So we have no way of measuring it. So what we're going to do is we're going to use a secondary and tertiary reactions to understand how fast this first reaction is. So this reaction, the first reaction 1, produces triiodide, this I3 minus ion, and then it feeds that into the second reaction as a reagent. Now here's the key. In the second reaction, we're always going to have the same amount of thiosulfate, and it will always be the limiting reagent. So if reaction 1 was 0th order, P was 0 and Q was 0, what that means is that the rate wouldn't change with the change in concentration. Of course, that would be really boring, and I can guarantee that's not what we're going to see. But if that was the case, we could change iodine, we could change the persulfate concentrations, and the amount of iodine would come out at the same rate, which means with the same amount of thiosulfate, we don't care about how fast this reaction goes. We just know it goes the same rate every time because we have the same amount of thiosulfate at the same temperature and the same phase every time. And so how quickly this reaction finishes depends on how quickly it gets its triiodide. And so the triiodide comes from this first reaction. So if this reaction slows down, then this reaction slows down. And so that's what we're doing here, is that we're measuring how quickly they can produce triiodide by how quickly this limiting reagent runs out. This reaction, when it goes well, it produces iodide, single iodide, which when reacting with starch makes no color change. But once our thiosulfate runs out, and it will always run out, then this reaction stops. And so then triiodide doesn't react with thiosulfate and instead starts to accumulate with the starch, and then it turns our solution black. And that's how we know then the reaction 1 is done. It's done producing triiodide at that point, and we measure that amount of time. And how that amount of time changes from run to run will either be 0th order if it's indifferent to concentration, 1st order if it changes linearly as we change concentration of both iodide and persulfate. If the rate changes linearly, then we'll determine its 1st order, and 2nd order if it's changing exponentially. So that's confusing. I'm going to give another attempt to explain this in an analogy form. So if you already get it, tune me out for a second, but if you don't get it, I understand. It's a little weird. So here's the idea. Imagine these boxes. This is some sort of assembly line, and these boxes are the reactions. So we're putting in I minus and our persulfate, and this reaction 1 is what we care about. When this comes through, it's making I3 minus, and it's making our sulfate, and it's going to dump to this next conveyor belt, and it's going to now move this way. So try to work with me on this analogy. It's dropping over here and going through reaction 2. So it's going to drop in I3 minus, and it's going to use this thiosulfate, and it's going to reproduce I minus. And because we're making I minus, reaction 3 doesn't work. So it's coming down over to here, moving through reaction 3, but I minus and starch makes no colored reaction. So again, we're going down here and then down here and through here, but no reaction because reaction 2 is eating up all of the triiodide. Then at some regular point, because we keep the concentrations the same, we run out of our thiosulfate. And so now reaction 2 fails, and I3 minus goes in one side and it comes out the other side. So now we don't have a change, and it drops down into reaction 3, which is now triggered. Triiodide with starch makes a colored solution, and we know that now reaction 2 has run out, which means reaction 1 has finished, or at least reached the same point every time, which is the point that our limiting reagent runs out. We time that, how quickly it takes for it to run out, and that's where we derive the rate. Okay, so let's dig into it. I'll show you what it looks like and what we're going to do with the data. We're just doing 5 runs. So here's our iodide that we're putting in, and our starch, that's our indicator. Do you have a question, Sophia?
Yeah, sorry. Just to imagine it, because I haven't really read the lab procedure yet. Does one happen next to the other? Do you have 3 different flasks where the reactions are happening, and then when it turns red, you know it's time to put on reaction 2, and when it turns the other color, you know it's time to put on the starch reaction?
Well done. That's a great question, Sophia. Really good question. The truth is they're all going to happen simultaneously, and that's the challenge that we have in understanding these reactions, is that there's all going to be one vessel, and it's going to, reaction 1 will go, reaction 2 will go till it runs out, and then reaction 3 will start. And we're going to mix all of the reagents together and then time it. And so, the actual data collection is very simple. It's very straightforward, and we're just collecting a time. And that's why I'm overemphasizing this, because there is intricate reaction steps, and we won't see it. We won't see ourselves mixing things and saying, okay, reaction 2 now, or reaction 3 now. We have to just understand that all 3 are going to be happening. And when we see a color change, when we finally see the end point, it's because this reaction has run out, which means this has, now started to accumulate I3 minus, which is now creating reaction 3, which is coloring our solution. And so we're going to stop it every time at that point. So I know that I'm probably not doing enough explanation to make everybody understand, but I think that by the time we do the lab, it will become more clear. But it's just going to be something that we're going to have to accept going in a little bit hesitantly, a little hazy with, but again, the post lab is really good. So
one more question.
Sure, Sophia.
The reaction 1 needs to stop before reaction 2 gives limiting reagent, or excess for reaction 3, or 1, 2, and 3, the 3 of them happen simultaneously?
Perfect. Let me just say this. Okay, so we're going to have excess I minus, and we're going to have excess persulfate, just ton of it. So if we left everything, this would run, let's say this could run for a week. Okay. The only thing that's limiting is the thiosulfate. So we'll put the same small amount of thiosulfate, this one with the X on it, with the same amount in there. If every reaction went the same rate, then we would produce this I3 minus at the same rate. Let's say it took 1 minute. The first time, the second time, the third time. That's a 0th order reaction. Then this would be dumped into here in 1 minute. This would run out in 1 minute. this would begin to accumulate in 1 minute, and this would turn, the solution would turn black in 1 minute. But what we'll see is we're going to change the concentration, first one and then the other, which because of kinetics will change this reaction, which will slow how much this triiodide is dumped onto this second conveyor belt, which means this will run out in a different amount of time, 1 minute and 30 seconds. And so then we will say, okay, by changing this concentration, this took longer to run out. How did we know that? Because after 1 minute and 30 seconds, this ran out, which means triiodide comes forward, mixes with the starch, and does reaction 3, which colors the solution, which I'll show you in just a second. And so that's how we're using the second reaction and the limiting reagent in the second reaction to monitor how quickly the first reaction happens, because we use the same amount, 10 mils of 0.01 molar thiosulfate in every reaction. If nothing changed the rate, this should happen at the same time every time, but it won't, because that would be boring. And so we'll be able to look at how changing these concentrations changes what time the solution turns color, which indicates how fast triiodide dumps into reaction 2, which is what we're monitoring from reaction 3. Does that make a little bit more sense, Sophia?
Yes, thank you. Thank you
No,
so much.
no, because I have been working for like 3 days on how the heck to explain this, because it is as complicated as it seems. Taylor, I saw your hand up. Do you have a question?
Yeah, would a good analogy be like a Rube Goldberg machine?
Yeah, it would be. Oh, yeah.
Okay.
But I don't know how many people understand Rube Goldberg machines.
Okay.
And the limiting reagent gets lost in that. But a Rube Goldberg machine is a simple mechanism, think of dominoes knocking blocks down, knocking books down, knocking things to turn a light on. So it's a very complicated series of simple tasks to do an even simpler task in the most complicated way possible. Check out Mythbusters Rube Goldberg machine on YouTube if you're curious, but it's pretty impressive. OK Go has a Rube Goldberg machine as a band, and that's very interesting. Nice comment, Taylor. So we're going to do 5 trials, and each time we're going to keep the volume the same. So we're going to make a flask A and a flask B. I'll show you in a second. And then to start the reaction, we'll mix them. So the total volume of our reaction will be all of these volumes put together. Please note that we have the same amount of thiosulfate in every reaction. That's constant. We have the same amount of starch in every reaction. That's constant. It's an indicator. And so in the first series of reactions, so trial A doesn't change either persulfate, so that's here, or iodine, so that's our 0 order. And then in 1, we're going to hold constant iodine and change persulfate twice. And then we will hold persulfate constant and change iodine twice, so that we can learn the order of each of those concentrations. Does it change the rate? But we're not changing starch and we're not changing thiosulfate. But why do I add these neutral, non-reactive salts to our solution? Who knows?
Are they like catalysts or something?
That's a good idea, and then catalyst would be an important aspect. It's actually the one thing I didn't add about rates. I should have had a 4th point, which was catalyst, but it's not. So actually what it is that when you have an ionic reaction, the ionic strength of the solution is very impactful, is very meaningful to the rate of the reaction. So if we would have reduced the potassium iodide and then just added water, the reaction would have changed for 2 reasons. Because spoiler alert, it would have changed because of the concentration change, but it would have also changed because of the ionic change. So every time we reduce the amount of one of our reagents, we replace it with a salt that is not going to be part of our reaction, either potassium nitrate or ammonium sulfate, but that has the same number of charges. So remember from last week, that same I value from the Van 't Hoff factor, right? How many charges it makes? What's the charge concentration? we keep that the same so that the ionic strength of the solution is the same, and also, most importantly, that the volume is the same, 65 mils each time. Okay, so I just wanted to give you this sense of what it actually looks like to see our endpoint here. So this is a starch solution reaching its complex. And so this is what in real life, if we were doing this, this is what our solution endpoint would look like. So this totally turns black. All right, let's take a look at what it looks like to collect the data. This is probably the easiest part. So I'm going to move pretty quickly through this. I'm going to highlight what you should be doing. But I think most importantly, you're going to see me checking off the reagents. And so keep in mind, we have every trial, you have to make sure that you have exactly the right concentrations. If you mess this up, all your rates will be messed up. And so none of it will make sense. So 5 trials, be very careful that you put the right reagents every time in the right flasks and add them. And so that you are able to have meaningful data. And so here we go. You'll see you need a couple of flasks, label them. So double click, and then instead of 150 mil Erlenmeyer flask, label them flask A and flask B. That'll be really important. You'll need a couple of graduated cylinders, a 50 and a 10 mil. So pull those out. You'll need keep everything off to the side because you actually need 2 constant temperature baths at 21.5, which is the automatic temperature. So you don't have to do anything for that, but just set 2 out. And so here we go. We're going to do trial 1, and we'll see everything that we need to add. So all of our reagents, are, of course, are on the top shelf, but keep track of what you're adding because everything is there and it's not always clear. You don't want to add a neutral salt instead of a reagent and wonder why your reaction didn't go. So 25 mils and add it to flask A. And so you can see I'm checking it off as I go, and then pour all the starch solution into the small graduated cylinder, 5 mils, pour all. And so we're just tracking it every time. A good suggestion as a group, have one person running the lab in your breakout room and have somebody else just be kind of the bossy person that says, okay, now do this. Okay, now do this. Okay, so that you have a double check that you don't need to redo your data later on if it doesn't make sense. So 25 mils of the persulfate and add it to flask B, pour all, and then of course your thiosulfate, which will be the limiting reagent on reaction 2, into flask B and pour all. And then you're going to put your 2 reactions into the 2 water baths. My recommendation is to stay consistent. So I marked here A and B, but in your lab, that's not going to be explicit, of course. But so my instinct as a scientist is to always have the left be A and always the right be B. And if you make that a rule, you'll know which is which. So make sure that you're consistent there. And then you just mix the flasks to start our reaction, our series of reactions. This is a very important part, and I want everybody to take a note of this. When I go to add from flask A, from flask B to flask A, as it's in the instructions, it'll give me this chance to say enter an amount or pour all. It will also pause the simulation, and you can read the time. So before you add them, you record the time as your initial time. This is a great moment in the experimental procedure before you add it to get the starting time. And you don't have to worry about pausing the simulation. So make sure you know this is the perfect moment to get the first time. And then you go until you see this. So I gave you that video of the endpoint because it is less clear in our simulation. This is the endpoint. This is what you should see. I'm just going to really illustrate this because if you don't see it, you need to. You won't be able to do this experiment unless you can see the endpoint. As soon as I see that color change, and one thing from doing this experiment a few times I noticed, the simulation does this weird thing. If you're looking really closely at this flask here, it flashes orange before it starts turning black. I think it's just a product of the HTML programming. It's not a big deal, but it's an indicator that the computer has told you it's reached the endpoint. And you wouldn't necessarily get that in real life, but at the same time, you would get, as we saw from the video, a much more clear black solution. So this is hard to see. So you'll want to be ready to know when to pause, and everybody's eyes will be right here and see that the volume is very low and the black is hard to see. Was there a question? Taylor, did you have a question?
Yeah. Do we take the temperatures?
You don't. So
don't.
if we were in a regular lab, then we would have a water bath and we would be monitoring the temperatures. But these water baths here, they're a constant temperature bath. So they keep this water at a constant temperature. It's given to us at 21.5. And because it's a simulation, we just assume perfection, that it's working. But the idea is that, I mean, because you're right, the temperature is really important in kinetics. And that's why we're keeping both of our starting flasks A and B at 21.5. And we're keeping our reaction as it goes at 21.5. So the temperature is constant, and that shouldn't affect the rate. So normally we would have a thermometer in here, but we're just going to assume it works perfectly.
Okay. And then when it flashes orange, that's when we measure
It's
the
like
time.
a second flash of orange. It's very, very faint, and then it turns black. So either look for that flash of orange, or obviously look for it to turn black or gray. And I assume that the endpoint for everybody will vary within a few seconds, and that's very fine. It's not going to go from clear to black. It kind of changes over a few seconds, and so depending on how quickly you can spot that will determine how accurate your exact number is. But because we're looking at a series of values, a series of rates, and the slope, then the math works out really nicely, and we'll all end up having, the same orders for our P's and our Q's. And then of course you're going to be pouring your waste out, and then this sounds like a silly thing, but you're going to be using a lot of flasks today. So make sure you remember you have to pour the waste out and then put it in the sink, because you will definitely not have enough room to do all of these runs if you're not doing this every time. Okay, so all you have to do today in total to complete this lab, you have to do that 5 times, of course, but with different reactants each time, right? So now we're varying our persulfate twice, and we're varying our iodine twice, and this acts as the first run for both the varying of iodide and the varying of persulfate. So we need to collect 5 delta Tn, so delta times. So that's the time that the color changed minus the time that the reaction started. Remember, we mixed those A and B, and I said before we push pour all, we collect that time. So that's the time the reaction started. The time we see the color change is the time it ends, and final minus initial gives us the time of the reaction. When we collect all 5 of those, we have all of the data we need to do the lab, but that's not nearly good enough for this lab because it is a challenging amount of work to do. But again, I just really want to emphasize how good the post lab is this week. So I want to just keep reiterating what we're doing. We're thinking about starting with reaction 2 in our data analysis. So triiodide is being fed into thiosulfate and making this iodide, which is non-reactive with the starch. So we always put the same amount of thiosulfate in, right? This one. So it's always completely consumed. It's the limiting reagent. Then because of that, we can, all of us, we know the molarity, we know the volume, we can determine the moles of thiosulfate, that's molarity times volume. And so we know the amount of triiodide because of this mole ratio here. We know the amount of triiodide it takes to reach that endpoint, to use up all of the limiting reagent. That will always be the same amount of triiodide. It just will take a different amount of time if reaction 1 is slower or faster. And then we can determine, because all of this kinetic math is in molarity, we can determine the molarity by dividing those moles from the thiosulfate and the triiodide by the total volume, by simply adding up all of the volumes that are in both of the flasks, because they're all mixed together when the reaction goes. 65 mils. And so, oops. So then we know the delta T. I just explained how we got that, final minus initial. So then we know how much triiodide was used up, same each time. Remember, same each time, no matter how fast the first reaction goes, we'll always have the same concentration of triiodide at the end point. But the delta T, if it's exciting, will be different. And that's what we will mainly be using to measure our rate, the change of concentration over the change in time. And because, again, because the source of I3 is this first reaction, so this is the reaction that we care about. This is what we're changing the concentration of iodide, changing the concentration of persulfate. So by measuring the change in the time that we reach our endpoint of triiodide from reaction 2, we're actually measuring the time it takes for the first reaction to produce triiodide, which is what we care about. And so we're going to, and I do have the real data for those people that are working, and of course all your lab instructors have the actual data, but if I showed it to you, it would really knock the wind out of the sails of this experiment. So this is a generic plot, but this is what we'll be plotting. We're going to be looking at the rate this is the rate law, so some rate constant times the concentration of iodide, the concentration of persulfate to the P and Q respectively. To find that, where we'll hold one constant, let's say we'll hold persulfate constant, so A is iodide. So we will hold this constant, so this goes away, and our rate equation is really just rate equals K, the concentration of I to the P. And then as we showed earlier from the math, we can graph it as the log of A versus the log of the rate, and the slope then equals P. So once we've done that twice, so we're going to do that for holding I, so holding the persulfate constant, find P, and then we can hold iodine constant. This becomes 1, and we can do the same plot and solve for Q. Once we've done that, we know P and Q. It's going to be 0, 1, or 2 for both P and Q. We can determine K each time because every time we did a run, every trial, we know how many of what the concentration of iodide, we know what the concentration of persulfate is. We know what the rate was because we measured it. So we can plug in the rate from our data. We can plug in the concentrations from our data. We can plug in the P and Q from what we just solved for. And that will feed us every of those 5 trials a K value. Of course, this should be a constant, so it should be the same for each run. But actually, the program is good enough to give us a little bit of experimental error. And so things kind of are a little bit hazy around that. And so you'll see that things aren't perfect. The rate constants won't be perfect. P and Q won't be exactly 0, 1, or 2. Expect that. But that's what you would see in a face-to-face lab. You would never see something exactly come out at 1, exactly come out at 2. The Ks to be all consistent. But they should be close enough. If they're wildly different, orders of magnitude different, then you really want to talk with your instructor. So here is a brief preview of the post lab. Again, trust the post lab is going to be there to really walk you through it, i.e., first off, what is the delta T for trial 1? And look at these values, 11, 31, 45, and 20. This just gets you to know whether or not what you measured as the endpoint is legitimate. I think it's a good starting question because if you measured 2 minutes and 45 seconds, like I did the first time, you got to go back to the beginning and say, oh, I'm not seeing what I'm supposed to be seeing. So this is a good place to start. And then take a look. So they're going to ask you total volume and calculate the volume from the reaction mixture by adding the contents of B added to the reaction to the beaker A. These should say flasks, but you get the idea. Report your answers in liters. So this is just, and every single question really has a good analysis backup. So it tells you exactly where you should be getting these values. So even if you collect all of the data the way I just explained, and you're like, I still don't fully get it, there's still help, so try not to panic. There's a larger table. This is very, very nice. If you can see up here, there is follow instructions for column E, follow instructions. So every single column in this table has specific instructions on how to collect the data. And by the time you go from the beginning to the end, you have a really good sense of all of the math, and it's much, much easier to do the graphs the way that I've described them because it's telling you to calculate it, then take the log of it, and put this in and calculate it and take the log of it and put this in. And so it really walks you through it. You're going to be making a graph. It's only asking you to do the rate versus the persulfate for the 3 trials. So that's 3 data points. It's 1 graph. So make sure that you understand that. Both graphs will have 3 data points. The first data point is going to be the same for each experiment, for each plot, and it's just trial 1. So it'd be trial 1, 2, and 3, and then trial 1, 4, and 5. Those would be the 2 plots. and the slopes of them will give you those coefficients. You only have to upload one. I think there are some mathematical ways that you can determine it, and there's some logical ways you can look at the data and understand the order when you see it. But I graphed them both. It wasn't very hard. It didn't take me very long, but you only need to upload one. Make sure you have everything graphed in the correct way. Make sure you have the axes labeled, the trend line, because you need that trend line because the slope, of course, is going to give you that coefficient. So make sure that you're taking a look at that, but you only need to graph and upload one. And then those orders of the individual, the iodine and the persulfate are asked for, and that's what you would get from that slope. And once you have those P and Q, then you can determine the rate law for the overall reaction. So let's see how fast this experiment goes. Questions? Real quick, because I got to throw you out to go to class. Any questions?
Could we go back and go the something about the salt, like adding the I can't remember.
Yeah,
specifically.
perfect. No, I got you. Yeah, I got you. This right here. Is this, Megan? Is this what you're talking about?
Yes. Sorry, I was muted. Yes.
Yeah, sure. Really good question. And one of those things that I didn't know how much to emphasize, but the idea is twofold, right? So we want to vary one concentration and then keep one constant. And then we want to vary the other one and keep the other constant. So two things can happen if we just add less. One thing happens is we have less total volume. That's not going to work because the molarity, and remember concentrations are what's important here. The molarity will change if we have different volumes. So we always have to have the same total volume. So all the starting molarities are the same, and hopefully it's only the rate that changes. But secondly, if it's an ionic reaction, a reaction that is dictated by ionic interactions, the overall reaction flask will have a certain ionic characteristic based on how many negative and positive charges, what concentrations of ions are in the solution. And that actually helps because of those intermolecular interactions, because ions have a really strong dipole, and that changes the overall, maybe I can say, intention of molecules. How much ionic strength is in the solution dictates how much the reaction goes. So we have to keep the ionic strength the same. So if we get rid of, let's say here, ammonium persulfate, we're going to add an equal amount of ammonium sulfate, which is non-reactive, but has the same +1. It's a 2 +1s for the ammonium and 1 2- for the sulfate, just like it's 2 +1s for the ammonium here and 1 2- for the persulfate. So overall volume, concentration, the ionic strength is the same in each reaction flask, even though the number of reagents that we care about, in this case persulfate, is allowed to decrease so we can study the rate. Does that make a little bit more sense?
Yes, makes a lot more sense. Thank you.
Yeah, thanks for asking it. Any other questions?
To add on to Megan's question, so you're basically saying when you put these salts in, they split, right? And since they have the same charge, they form with the other to kind of neutralize it? Is that
They're just there,
like bouncers at a club, or like?
Yeah, it's something. I'm kind of thinking the same way. I'm thinking like if you were experimenting at a party and you had 100 people at the party and you put 10 mean people in the party, and then you're like, okay, what happens if I put 20 mean people in the party? But you have to have the same number of people for the experiment to work. So we're changing the reactants, but we have to keep the number of ions the same because that will also change the rate. So we're just keeping the total number of ions the same. So between the two of these, there is the same number of plus and the same number of minus, and they're very similar in nature, the ammonium and their sulfates. They have the same 2- and +1, but the active reagent, which is this guy and which is this guy, those are changing. So the reaction rate can change, but the the environment, the number of people at the party, the number of ions, and the strength of the ions stays the same in each reaction.
Okay, that makes more sense now. Okay, thank you.
Bouncers at a club, though, I like that.
Thanks.
Any other questions? I got to send you off to class. Anything else? Okay, you guys are fantastic. If it's tough to understand, I get it, but your instructors are going to be well prepared for you. It's not as bad as it might seem. Thank you everybody for your attention. Enjoy your week and have a good lab.
Thank you. See you on Friday.
Okay, see you.
Thank you.